Hello everyone, in this section we are looking at optical sensors and Sentinel-2 optical remote sensing deals with the part of electromagnetic spectrum that is characterized by the wavelengths, from the visible to the near-infrared up to thermal infrared, imaging reflected and emitted radiation from the observed surfaces. And it can be passive sensing or active sensing. Passive sensing will mean that it is going to use the external illumination body. And with active sensing, it means it is going to provide its own source of light. And it can be multispectral or hyperspectral. Sentinel-2 is one of the products of the joint forces of the European Commission and European Space Agency called Copernicus. It carries an optical payload with visible, near-infrared, and shortwave infrared sensors comprising 13 spectral bands with a swath width of 290 kilometers. The mission orbits at a mean altitude of approximately 800 kilometers, and with the pair of satellites in operation. And it has a revisit time of 5 days at the equator, that is under cloud-free conditions, and 2-3 days at mid-latitudes. The 13 spectral bands guarantee consistent time series, showing variability in land surface conditions and minimizing any artifacts introduced by atmospheric variability. And a snap which can be found here, is an open-source common architecture for ESA toolboxes ideal for the exploitation of Earth observation data. The infographic here represents an overview of the Sentinel-2 mission, so take a look at it. The multispectral imaging capability of Sentinel-2 makes it useful for land cover, land use, and land use change detection task. And it is also good for risk mapping, degraded forest and habitat analysis, distinguishing healthy crops from diseased-affected ones, distinguishing healthy trees and dead ones due to its infrared bands. It can also be used for water management and soil protection, and also for terrestrial mapping for humanitarian aid and development. Earth's surface objects absorb and reflect different amounts of energy at different wavelengths, and the magnitude of energy that an object reflects or emits across a range of wavelengths is called its spectral response pattern. The three important spectral regimes in remotely sensing of vegetation are visible, near-infrared, and shortwave infrared. Normalized difference vegetation index is a dimensionless index that describes the difference between visible and near-infrared reflectance of vegetation cover and can be used to estimate the density of green on an area of land. Its usage has been so widespread that the normalized difference concept has been applied to numerous other areas of remote sensing, including the detection of snow soil properties and the classification of clouds. For instance, in the visible wavelengths, the majority of solar radiations are absorbed by vegetation pigments. A slight reprieve in absorption exists in the green wavelengths, around 540 nanometer, explaining why most plants are seen as green by humans as they reflect more green radiation than that of other colors. Due to equally spaced over time and consistent revisit of 5 days at the equator capability of Sentinel-2, we are able to easily generate trend analysis of the various signatures imaged and be able to make forecasts and predictions based on the historical records. A time series of vegetation index images can reveal changes in crop health over a large geographic area or within specific fields. The most effective use of the NDVI is in time series analysis. By recording successive NDVI snapshots of the globe or a smaller region of interest, one can track changes in vegetation both spatially and temporally. Satellite-based imagery time series analysis helps to track what, when and where changes have occurred at global and local levels. The image as shown here shows track changes of the degrading forest and the crop fields. Here is a list of references for further reading. Thank you for your attention.